right, let's go ahead and get started. Welcome, everyone. There are some seats for those of you standing on the side if you want them. You can also stand on the side. It's good. Cool. So I'm talking about parallel Ruby and how it eats all of your memory and some magic to stop it from eating all your memory. Cool. So some background on myself. So my name's Kevin, and I work at a company called Flexport. And our mission, we're in the freight shipping business, and our goal is to make global trade easier for everyone. So this matters for two reasons. One, it's a shameless way for me to plug my company, using my platform to do that. But more importantly, we run a lot of background jobs because, there are a lot of boats, planes, trucks we're tracking at all times. And trying to keep track of all these things requires running a lot of, cron jobs, a lot of stuff in the background just to, scrape from various sites, hook up to GPS devices we have plugged into trucks, all sorts of things. And we end up doing, this. I pulled this during lunch this morning. So we end up doing around 7,000 jobs a minute, peaking to around 20,000. That's about 350 a second. But what's important about this is that these are almost all I/O-bound jobs. They are make a network request to something to figure out where something is. Go figure out where a boat is, or a truck, or a plane. The trucks and planes are more interesting. The boats are in the middle of the ocean, and they stay in the middle of the ocean. So we used to run all of these jobs in a single process world. We had about 20 servers, each with running 12 Ruby processes. We were running Sidekick. If any of you have used it, it's awesome. But we didn't necessarily trust ourselves to be thread safe, so we were ignoring all of the benefits of Sidekick and running single-threaded, one process, 20 servers, 12 processes per server, 240 Ruby processes. These are I/O-bound jobs. So just as an aside, for everything I'm talking about here is going to be specifically about C Ruby, MRI, Ruby you're probably all used to using. And in Ruby, there's a global interpreter lock. Only one thread can run at a time. But since these are I/O-bound jobs, we should be using threads here. Like, they're waiting on a network request. They don't need to be running. So we did a big migration. Have the number of servers, great, we save money. My boss is happy with me. Pump up, run way more threads, and be able to do a lot more work. So what happened? This is the best graph I can find looking through our server logs. And you can see the runtime of these jobs just gets slower and slower. The green bars are new deploys. So new deploys come out, and the time drops. They get slower and slower again. Lunch was terrible. No one deployed during lunch. So it got really bad. New deploy came in. So the goal of this is to try to dive into what's going on, why are our jobs going slower and slower. But there's one important side note I want to talk right here, which is if you deploy every 10 minutes, you can ignore a lot of problems. Like, when people talk about CI/CD, you get a lot of benefits by just having things restart every 10 minutes. This is not the point of the talk, but very, very good life lesson. All right, now back to actual business. So I don't want to go into the actual code because that's confusing, and no one can actually dive into any code base and understand it. So I'm going to do a dummy code instead. So what this is doing is it's spinning up a bunch of threads, 20 threads. Each thread is sitting in a loop. That loop is allocating some memory and then not returning anything. So it's just chucking that away. So if we look at this, each thread is just in a loop allocating a 1,000 element array with each element in that array being a 1,000 character string. So just 1024 A's, and we have 1024 of those. We have about 1 million characters. So let's go ahead and run this. And we're also going to monitor the memory. So this is going to be memory in megabytes. And we can see it starts going up really rapidly. And it keeps going, keeps going. I could let this go for a while. It drops because garbage collector, cleans up some of it, but it's still going up even with the garbage collector going. This isn't super easy to read, so I've also, did a run previously and graphed it. So you can see the garbage collector is running. Any ideas what's going on here? So, is it a memory leak? So if it was a memory leak, you would expect this to keep going up and up and up over time. But what we see instead is like a logistic curve. Instead, this is close. It's memory fragmentation. So to understand memory fragmentation, I want to take a little bit of time and talk about how memory works in Ruby. I'm not going to go into all the details because I only have 40 minutes, and that could be hours of talks on its own. But let's go over the high level of how memory works. So at the first level, Ruby manages its own memory. So Ruby manages memory through the idea of a Ruby heap. This is going to be very different from the idea of a C heap, which we'll talk about in the future. They're both called heaps. It's really confusing. I will try my best to be very explicit about which heap we are talking about. We're talking about Ruby heap. So the Ruby heap is arranged with a lot of 40-byte slots. So whenever you allocate any object, it goes into one of these 40-byte slots. And everything can go in here. So this is where strings will go. This is where classes will go. This is where hashes, arrays, integers, but bigger integers, like integers less than a certain number for performance reasons are just stored in well-known memory addresses. But in numbers, floats, whatever, regular expressions, you name it, it gets stuck in one of these slots. So when we're allocating one of these arrays, well, an array is something, and everything that's something goes in a slot, so it goes in one of these slots. But these slots are 40 bytes. That thing's bigger than 40 bytes. It doesn't fit there. So to store anything that's bigger than 40 bytes, which most things are, there is the C heap, totally different from a Ruby heap. This is OS heap, C heap, whatever. I'm going to refer to it as an OS heap because C is both a letter and a word and is unclear what I'm saying. So this is going to be OS heap. And these are organized in just 4 kilobytes of space. Whereas the Ruby heap are nice, delimited 40-byte chunks. The C heap, you can put whatever you want. Just chuck it in there. You got 4 kilobytes of pages. You can have as many pages as you want until your computer segfault or crashes, or if you have Windows, blue screens. But you can put anything you want here. So when we allocate this array, first we have our array slot, and that array slot is going to use those 40 bytes to tell you where in the OS heap to actually find that array. Everyone with me? Yeah. So, but each of these array is an array of strings. Each of those strings needs a slot. But all of those strings are also bigger than 40 bytes. So those strings are going to, in turn, refer back to the actual strings themselves will be in the OS heap. So we're going to have a lot of pages in the OS heap to store all of the actual strings, and then the Ruby heap will just have all of the slots saying where to go find them. Cool. So as an aside, let's talk about how much memory we think we should be using. So it's always interesting to say, how much memory should we be using, and then realize how in practice that is never reality. So we know on the Ruby side of things, we know we need 1 slot for the array and 1 slot for each string. So we should end up with 1,025 Ruby slots. And because it's 40 bytes a slot, the total size in the Ruby heap should be about 40 kilobytes. The OS heap, on the other hand, it actually stores all of the data. It's a lot bigger. We end up with, around a megabyte is what we'd expect. And then if you remember, this is happening for each thread. So we'd expect, 20 threads, so around 20 megabytes, except, the garbage collector doesn't run, it runs sporadically, so let it add up a bit, maybe throw in some overhead. Let's just say 10x. So, because, let's just multiply it by 10. That gives us a good number. We expect our memory to be around, a couple hundred megabytes. Clearly, it's not. This is what is that? Like 10x what we, is 10x the right number? No, like 4x what we'd expect, which is, never nice when your memory is 4x what you expect it to be. So what's happening? Well, the way I laid this out assumed things were nice. But in reality, this whole 1024 byte array, it's an array. It's a chunk of memory. It needs enough room for that entire chunk. If it doesn't have enough room, like say this first page just has, some memory but not enough to allocate the entire array, that space is just wasted. We can't put anything there. So what we end up with is just a lot of wasted space in the OS heap. I want to be very clear here. This is not the Ruby heaps problem. Ruby is awesome. Ruby has no problems. Never let anyone tell you Ruby has anything wrong with it. This is totally C's fault. So going back to our example, this would already be bad, but this talk is about parallel Ruby. So where does parallel come in here? And it turns out Ruby threads are not very memory friendly. When we're doing this for each thread, we have our thread, we have our fragmented OS heap. Remember, we just talked about how our OS heap can get really fragmented. Your Ruby heap can too, but it's much less likely because every single thing is 40 bytes. It's very easy to, when everything's the same size, it's very easy to fill in gaps. When you have multiple threads, you would think that they would just share the same heap. After all, Ruby, again, remember, Ruby has a global interpreter lock. You can only run one thread at a time. But we're talking about C land. C doesn't know that. In C, you can run whatever you want. So C is trying to be helpful and think, hey, two threads trying to allocate memory in the same heap, that can cause contention, that can cause performance problems. Let's not do that. So instead, each thread gets its own heap, OS heap. And so all 20 of our threads have their own fragmented OS heap that's just getting more and more fragmented over time. And that is why we get our memory problems. That is why if you ever try to run multi-threaded Ruby, you'll just see your memory just go way higher than you'd possibly expect. All right, so now we know the problem. Let's actually talk about useful ways of fixing this. So, option one, let's just not have one heap per thread. Again, I've said this like 5 times now, but it's still true. Ruby has a global interpreter lock, ignoring Ruby 3 and guilds and all the cool stuff Mats talked about yesterday. Ruby has a global interpreter lock, one thread at a time. There's no point in having more heaps. So this can actually be configured. This can just be configured with an environment variable. You can set, the OS heaps are also commonly referred to as arenas. There's a lot of terms. So you can just set this with an environment variable. So I'm going to run the exact same program, but I'm just going to set malloc arena max equals 2. Exact same thing. Oh, hey, look, it's better. If you remember before, it jumped up to over a gigabyte pretty immediately. Here we're staying at around 700 megabytes. 600, yeah, garbage collector is doing its work. So again, I plotted it because graphs are much easier to understand than streams of numbers. And we see we have about, what is that, about half the memory usage. It's a lot more stable. Great. So yes, what key takeaway here? Set a magic environment variable and everything's better. There is an open ticket as part of, on the Ruby forums to make this variable default in Ruby. And maybe it'll get accepted. Probably won't, especially with the actual threads and guilds coming up in Ruby 3, but we'll see. Option 2. We can use a different memory allocator. So by default, we're just using the standard C memory allocator, malloc. There's no reason we need to use that memory allocator. You can, it's as long as it adheres to the C API, we can do whatever we want. The one I'm choosing to use here is JEmalloc. The reason, there's a lot of other ones. I like JEmalloc because, well, one, the Sidekick author very much promotes it, and I like blindly following other people. Another, it's gotten pretty wide adoption. It's the memory allocator that Rust uses by default, so Firefox uses it. It's the memory allocator Redis uses, so it's pretty tried and true. This is a little bit harder to do. You actually have to install Ruby with a configuration option to actually be able to use this, which I've done because what's the point of a demo if you can't do it? But once you've installed it, you can just set another environment variable that's slightly more complicated. Yeah, look at that. Yeah, we're way better. So yeah, magic environment variables, they fix everything. So again, if we graph here, we got, yeah, we're actually below my random expectations that I drew. So we're sticking, we're well below the defaults. So again, well, the first takeaway is use continuous deployment, and then none of this matters. But the second takeaway here is anytime someone complains about, Ruby using too much memory, consider throwing some, out-of-the-box environment variables at it and see if your problems go away. Cool. So what should you do? So this is a big tale. I'm not going to read it. But the main answer is, how much control do you have? If you have no control, you can't do anything, this is a black box, then yeah, you're stuck with the defaults. If you have no control and you're using a black box and you don't have anything you can do, you're probably not running Ruby anyway. So if you have some control, like say you're using Heroku and you can set environment variables, then you should almost certainly be setting your max arena count. Although if you're using Heroku, you don't have to because this is now default on Heroku because they realized, wait, we control it. We can just do it. So yeah, Heroku, you already get this for default. And then if you actually have access to the underlying servers, you can configure your Ruby. Highly recommend JEmalloc. It's basically just when you install Ruby, you just pass in a command line argument. It supports it. Downside being it's Linux only. So all of you Windows Ruby users, I'm sorry. This talk isn't for you. I apologize. Cool. Yeah, so if you control, JEmalloc is just awesome. If you don't, well, you should pretty much always set malloc arena max. You can set it to 1. Again, Ruby, global interpreter lock. So you can set this to 1. In practice, I actually tried doing a demo with this at 1. I got a little bit better performance using 2. If I was actually very invested, I would have looked more into why, but then I realized that I had to give this talk in a week, and so I didn't. But someone knows the answer. I'd love to hear it, why 2 is better than 1. And I'm not the only one who thinks this. So on the actual Ruby forum trying to make JEmalloc the default, there's such comments as, this is from the Sidekick author saying, hey, people say they have memory problems. I tell them to switch to JEmalloc, and suddenly a miracle occurs. They no longer have memory problems. Other things on the same thread, just doing this gave me not only a memory speedup, but also an 11% performance boost. As any good programmer, you should immediately look at that and think, well, that's for their use case. Benchmarks never really work out, but it's still nice to put. And another great one, I used to have memory problems, and then I switched. Cool. And yeah, then this is all from the Ruby Lang issues trying to make this standard. It wasn't accepted as part of the language for a lot of good reasons. Mainly, it's kind of weird to add default behavior that only works on a single operating system. It makes Ruby less portable, stuff like that, but doesn't mean you can't do it. Cool. And I had more on this talk, talking about other ways to reduce garbage collecting, and then I saw that Aaron Patterson is giving a talk exactly on that topic tomorrow. So instead of listening to me talk, let's listen to someone who knows way more about this talk and go to his talk instead. Cool. So that was what I had, and thanks for listening to me rant about parallel Ruby. Yeah, good question. Sorry. The question was, is there any reason not to set malloc arena max to 2? Like, if you are, and the question was if I'm using shuriken or another multi-threaded library, should I just always set it to 2? The only reasons not to, one, if you're using JRuby, which has real thread support, or 2, if you're trying to experiment with some of the Rails 3 guilds. But besides that, no, you should always set this to be that. Yeah. The default depends on, it's operating system specific, but on Ubuntu, it's 2 times the number of processes. So I'm running this on an 8-core machine, so it's running 16 is the default. Oh, sorry, I do apologize. The question was, what is the default value for the malloc arena max if you're not overriding it? And the answer is, generally, it's a constant factor times the number of cores. Generally 2, I think, is for Ubuntu. And the reason being, if you have real threads, you want to say, okay, you got to balance between memory use and CPU use, and 2 is a good number. Yes, so I did compare. I have another chart. You would think I would be, 3 times, you would think I would learn. Nah, I'm going to keep having this problem. The question was, all right, I tried 2 arenas. I tried 1. How about 3 or some other number? And yeah, I tried a bunch. You basically get what you'd expect. Whereas if we go back to this graph, remember the yellow is with 2 arenas, the blue was with the defaults. It just keeps creeping up and up and up. It increases, I don't want to say linearly because it's already a logistic curve, but it plots exactly as you'd expect, gradually changing from yellow to the blue. With 1, it stays right about where the yellow is. It just gets a little slower performance-wise. Yeah, the question, I got it this time. So the question was, what about setting the arenas on jemalloc? So the idea of arenas is specific to glibc, the GCC, the C, classic C memory allocator. jemalloc doesn't have the idea of arenas. That's one of the reasons it's better for memory. It has the idea of runs instead, which are very similar, except they can be shared more easily. And sorry, this is getting way too many details, but you don't need arenas with jemalloc. This will work on any flavor, anything that uses GCC as its, or CLang or whatever, any flavor of Linux. This will work on. This is not specific to Ubuntu, which was the question. Yeah. So the question was, do you want to set all these environment variables globally? And it depends on what you're doing in your Docker container. And for the sake of this example, I actually did because it's a toy example. It depends on what else you're running, but yeah, it can affect other things. So generally, I would caution you to only apply this to, in general, if you're messing around with environment variables, you should scope them to a single program. But people do. There's probably no harm. Just don't come yell at me if it crashes everything. So the question was, should you use jemalloc if you're not using threads? So I have done this because we run, in addition to these Ruby threads, we run a Rails application, which we do run single-threaded. And even with that, we saw about a 15% reduction in memory usage from switching to jemalloc. So nothing nearly as dramatic as this, but there was still significant memory savings, even in a single process. So I'd still recommend it, but your mileage may vary. Again, never trust a single person's benchmarks for anything. Yeah, so the question was, can I explain how jemalloc works? Without going too much into it, mainly because I don't want to say the wrong thing, because I tried reading the source code for this, and it turns out C is a little hard to read sometimes. Who knew? But the idea is that when we look at the pages, when we look at these page ideas, so normally when you allocate memory, everything is organized in these 4 kilobyte pages that every time you want memory, you get a chunk of those page. If you run out, you get another page. For jemalloc, instead of allocating in full pages and giving each thread its own page, it does sections of pages that it calls runs, and it allows those to be split up and shared among threads. Is my understanding. So someone in here has got to actually know what they're talking about and just glare at me. Yeah. So we did see, so what actually prompted this whole investigation and dive into all of this, sorry, this is a little bit of story time, is, so the question was, going back to the former idea of, continuous deployment is great because you don't have problems. Well, and the question is, well, did I try and see what happens if I let this run longer? So what actually started this, if you look to the left, you'll see before the day started. And it's really bad. And so what actually prompted this whole investigation is we have an engineer who works in Vietnam. One of our first engineers, incredibly prolific engineer. He's constantly writing code. He came out and visited the United States. Vietnam has about a 9-hour time zone difference. So we're deploying 24/7. When he came out and visited the United States, no one was deploying at night. Yes. When you learn things that can go wrong, that is what prompted this whole investigation and learning way too much about all of this. He's not allowed to come visit the United States now. Cool. Well, that was my talk. Thank you guys all for showing up, and hope you have a great rest of your day.